Okay. In the last class, I present the construction of a cubic sprite function. The construction was very tedious and complicated. So clearly, the approach cannot be extended to construct sprite function of higher degrees. Okay, then how to solve the problem? Now, today I present one approach to solve the problem. I want to find a sprite function of any degree. Okay. First, take a review. The definition of a sprite function. Yeah, I always emphasize definition, especially in mathematics. Yeah. Okay. Sprite function. Yeah. Given an interval AB. Yeah. And cut the interval into subintervals. T0, T1, T2, Tn minus 1, Tn. Now, over each subinterval, build a polynomial of degree k. Again, polynomial. Yeah. The first subinterval is a little bit tricky about this definition. The first interval is not from A to T0, but from A to T1. So yeah, here open A to B, this interval is open interval. A to T1, polynomial. Yeah, polynomial. Yeah. According to the book, denote the polynomial by S0. This is a polynomial of degree k. And then T1 to T2. And T1 interval is closed. So solid point here. Second polynomial. This is the S1, and so on. The last subinterval is not from Tn to B, but from Tn minus 1 to B. Okay, a little bit tricky. Yeah. So a function in this space, actually, this is a space. A function in that space is piecewise polynomial, and also and also smooth k minus 1 from A to B. Derivative of order from 0 to k minus 1 exists and continuous over the interval A to B. This is a definition. This is a review number 1. Second review. This is a review number 1. Second review. Yeah. In the last class, I introduced truncated power function. Truncated power. A power function. X minus, say, let me pick a lot here. T0 to Tn. Let me pick a lot. Say, Tr. Okay, Tr. This is a power function. Yeah, this is a power function. Now, truncated power function definition is when x greater than or equal to Ti, truncated power function is the power function. When x less than ti, 0. Yeah. Turns out that this function plays a key role in the construction of spline function of degree k. Now, turn to today's topic. The set of all spline functions of degree k is a space. What it means, space. This is a mathematical term, okay? Yeah. S and K is a space. That means, yeah, from this set, arbitrarily pick two functions. Yeah, pick two functions. S hat from this set. Right. And AB, two numbers, real numbers. Okay, two real numbers. Then a linear combination of these two functions, AS plus B, S hat, still in the set, okay, not outside the set. Yeah, from the set, arbitrarily pick two functions, arbitrarily pick two real numbers, then linear combination still in the set. Yeah, with this property, then the set is called a space. Space. Say Rn, yeah, R2 is a space. Yeah, R2. Two-dimensional space. R3, three-dimensional space. Yeah. This is the set of all the points on the plane. Satisfy this property. This is the set of all the points in space, three-dimensional space. Satisfy this. Space, two-dimensional, three-dimensional. Now, this is a space. Now, let me determine its dimension of this space. Okay, yeah. Okay. Okay, first, let me prove a lemma first. Lemma. Then I present the dimension of this space. Lemma. Okay. The following n plus k functions. These functions from this space, the set of all spline functions of degree k, are linearly independent. Yeah. What it means, linearly independent. In linear algebra, yeah. In linear algebra, say k vectors, vector 2, vector k are linearly independent. what this means? This means this equation has only one solution. C1, C2, scalars, CK. This equation has only one solution. The solution is C1 is equal to C2. CK is 0. If this equation has more than one solution, then we say that these k vectors are linearly dependent. Say more than one solution. Say for example, just for example, okay. C1 is 0, C2 is 1, C3 is 2, and C4 0, and so on. Suppose this is a second solution of this equation, then we will see some vectors depends on other vectors. Why? Plug the solution into the equation, then we get 0 V1 plus V2 plus 2 V3, then plus 0 V4, and so on. 0 Vn, Vk is 0. Yeah. Suppose this equation has a second solution, then I plug the solution into the equation, then I get this equation. All right, now, how about rewrite the equation? I keep V2 on left side, move all the terms to the right side. Then we have V2 is negative 0 times V1. Of course, it is 0. Minus 2 V3. Minus 0 V4. Yeah, and so on. Minus. Yeah. Then this last equation says that V2 linearly depends on V1, V3, V4, and Vk. Yeah. If this equation has more than one solution, then one of the k vectors linearly depends on the other vectors. Okay, now extend this concept to functions. Yeah. Each element in this space is a function. Now extend. Okay. Yeah. The following n plus k functions are linearly independent. Which n plus k functions? Yeah. 1 is a polynomial. Yeah. X polynomial. X square polynomial. Okay. Now this space piecewise polynomials of degree k. So okay. Xk. Yeah. Let me see how many functions. K plus 1 functions. Okay. Now, okay. Now next, x minus t1 truncated k. Okay. Yeah. Pay attention. Not x minus t0, but minus t1. This function, we have proof it is in this space. Okay. Okay. Now, in here we have k plus 2 functions. Okay. Now continue. X minus t2 truncated k. Yeah. Then x minus t n minus 1. Yeah. Pay attention. Not x minus tn. How many functions? From 1 to tk, k plus 1 functions. Yeah. In total, how many functions? I believe n plus k functions. Yeah. Here, K plus 1, so many functions. How about here? Here. Here. N minus 1 functions. N minus 1 functions. So the sum exactly N plus K. These N plus K functions, it turns out they're linearly independent over the interval from A to B. Yeah. The proof not difficult. Okay. Yeah, the proof easy. To show that these functions are linearly independent, we need to solve the following equation has only one solution. Yeah. Which equation? Yeah, this one. Okay. Alpha 0. What is alpha 0? Unknown. Times 1. Yeah. Yeah, times 1. 1 degree is 0. So alpha 0. Now, alpha 1 times x1. X degree is 1. So alpha 1. And then alpha 2 x squared. Alpha k xk plus now plus scalar some number times this, okay, plus beta 1 x minus t1 k truncated beta 2 x minus t2 truncated k and and beta n minus 1 is 0. This equation has only one solution. Which solution? Alpha 0 is 0. Alpha 1 is 1 is 0. Okay. All coefficients are solution. Yeah. I want to show that this equation has only one solution. Okay. Now, first, let me solve. Okay, first. I want to show that alpha 0, alpha 1, alpha k must be 0. Okay. How to solve this? Easy. Okay. In the first subinterval, the first interval is what? Is A to T1. Okay, not A to T0. A to T1. Yeah. Okay. Okay. Alpha 0, alpha 1 to alpha k. This is k plus 1 unknowns. Let me take, okay, distinct parts. X0, x1 to x k. Okay, take this. Yeah. From this equation, I pick x0, x1 arbitrary pick. Okay, and make sure these points they are different from each other. Okay. Now, I plug in this point into the equation. Let me call this equation 1. Okay. Yeah. Okay. Plug in. Okay. Plug in the points in equation 1. Okay. Equation 1. Plug x0 in equation 1. Then we get alpha 0 plus alpha 1 x0 plus alpha 2 x0 squared alpha k x0 k. Yeah. And then what? Here. Part x0 in this x0, k. Yeah. We need to recall the definition of truncated function. X0 less than T1. So truncated function is 0 by definition. Okay. And also this is 0 definition. Okay. You need to go back to the definition of truncated function. So all 0. So this equation becomes 0. Similarly, x1 in x, we get alpha 0 plus alpha 1 x1 plus alpha 2 x1 squared. Alpha k x1 k is 0. Plug in xk, then we get alpha 0, alpha 1 xk plus alpha 2 xk squared. Alpha k xk. This is x1 xk k. But this linear system has only one solution: 0, 0, 0, 0. Why? Because write this in linear system in matrix vector form. Yeah. Let me write the linear system in matrix vector form. 1 x0 x0 square x0 k 1 x1 x1 square x1 k and 1 sk sk square xk k. Yeah. A0 A1 A2 AK is 0. This linear system has only one solution: 0, 0, 0. No other solution. Why? Because coefficient matrix non-singular. How to know coefficient matrix non-singular? Compare determinant. Okay. Yeah. Determinant of the coefficient matrix. This is well known. Okay. How people call this matrix? Random matrix. Its determinant is well known. Okay. It is x0 minus x1, x0 minus x2, x0 minus xk, and then times x1 minus x2, times x1 minus xk, and so on. Then the last is xk minus 1 minus xk. A product of the difference of different x values. Yeah. So because we assume x0, x1 to xk, they are distinct to each other. So this product non-zero. It's a non-zero. Coefficient matrix determinant is non-zero. This matrix non-singular. It has inverse. Okay. Now move this matrix to the right side. Only one solution: 0, 0, 0. So solve this linear system. Then we get alpha 0, alpha 1, alpha 2, all are zeros. Now next, I prove beta 1, beta 2, beta n minus 1, all are zeros. Okay, now. Yeah. Yeah, I still call this equation 1. Okay. Now I know alpha 0, alpha 1, alpha 2 to alpha k. They must be 0. Okay. No other choice. Okay. Then equation 1 becomes 0 times 1 plus 0 times x plus 0 times xk. Then plus beta 1 x minus t1 truncated k. Beta 2 x minus t2 truncated k. And beta n minus 1 x minus x t n minus 1 k truncated is 0. Now next, I prove beta, all the betas must be 0. Now this time, easy. How? Take a number, say, take say take x be say t2, okay, t2. Now plug in t2 in x, right? Then we get 0, right? Yeah. The first k plus 1 terms, they are all zeros. Beta 1, t2 minus t1 truncated plus beta 2, t2 minus t2 k, yeah, truncated. Beta k, m minus 1, t2 minus tn minus 1 k, truncated is 0. Okay, now by definition, yeah, you need to always remember definition of truncated function. This is equals to t2 minus t1 to power k. How about this? This is 0. And this is 0. So this equation is beta 1 times non-zero number is 0. Beta 1 must be 0. Implies that beta 1 must be 0. How to solve? Beta 2 is 0. Set x to t3. Yeah. Here I set x to t2, then I got beta 1 0. If I set x be t3, then plug t3 into the equation, I have beta 2 0. In this way, I can prove that beta must be 0. Therefore, this equation has only one solution: 0, 0, 0, 0, no other solution. So we prove that these n plus k vectors are linearly independent. N plus k vectors are linearly independent. So dimension of S n plus k greater than or equal to n plus k, because in a space we have at least n plus k linearly independent functions. So the dimension of the space greater than that, greater than or equal to at least. Now next, I want to solve dimension of this space exactly n plus k. How to solve? Is very mathematical. Now, next, I want to solve. Okay, next, I want to solve. Okay, dimension of S and K must be equal to M plus A. Right. Now, how to solve? Right. Right. It is the main theorem in section 6.6. Yeah, this is a theorem. The dimension of S and K is equal to N plus K. In fact, what is dimension of a space? The number of elements in a basis is dimension of the space. In fact, the functions, yeah, from the lemma 1x, x squared, xk, and x minus t1 truncated k, x minus t2 truncated k, x minus t n minus 1 truncated k. In fact, this n plus k functions is a basis, okay, from a basis of this space. In the lemma, we prove that these m plus k functions linearly independent. Now, I want to solve any function. I want to solve. This is a basis. What it means, a basis. Any function from this space can be written as a linear combination of these m plus k functions. Okay. Now, proof. Arbitrary. Hey, a function. Say give a name. Okay, say S from the space. Okay. Arbitrary pick. Okay. I want to solve. S is a linear combination of these functions. Okay. Because this S was chosen by me, so I know this S. Okay. It is a piecewise polynomial. Okay. S is a piecewise polynomial. Okay. Over the first interval a to t1. Okay. It is a polynomial of degree k. Yeah. I pick this function x, so assume I know this polynomial. Okay, everything I know. Okay, I know. Okay, I know. Over the second interval is t1 to t2, close at t1. The polynomial is t1. Hey, suppose I know this polynomial. Okay, I know. Okay, and so on. Okay. The last subinterval is Tn minus 1. Okay, not Tn. Okay. Tn minus 1 to b. The polynomial is Pn minus 1. Okay, yeah, I know this. Okay, because suppose I know S. Okay, now S is arbitrarily chosen. I want to express this S as a linear combination of these functions. If successful, then these functions is a basis. And the dimension of this space is n plus k. Okay, now I try to express this as a linear combination of the functions. Okay, write S as a linear combination of the functions. Alpha 0 times 1, alpha 1 times x, alpha 2 times x squared, alpha k xk plus beta 1 x t1 truncated k, beta 2 x minus t2 truncated k, beta n minus 1 x minus t n minus 1 truncated k. What is alpha and beta will be determined. At this point, I don't know. 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 I want to not determine alpha and beta. Okay. So that this equation is true. It's true. Okay. So okay. Consider this interval first. Consider this interval a to t1. Over this interval, left side is P0. On this interval, S is P0. Right? P0, I know P0. I know this guy. Okay. Now, over this interval, for any x between A and T1, right side is alpha 0 plus alpha 1 x, alpha 2, alpha k, xk. And then plus beta 1 times 0. Right? You agree? When x between A and T1, this must be 0. Definition of truncated function. And also this is 0. Yeah. Plus beta 2 times 0. Beta n minus 1 times 0. Right? Alpha unknown. Okay. Unknown. Okay. This equation implies that P0 is A0, A1, AK, SK. A0, I know. Okay. Now the right side is unknown. Alpha unknown. Alpha K unknown. And then the remaining terms all are zeros. Now, how to set alpha? Okay. How to set alpha? The only choice is set alpha to be A0, alpha 1 to be A1, alpha K to be AK. Yeah, I want to find alpha and beta so that this equation is true. Now, first, I consider x is in this interval. Then S is P0. The right side is this. Now, how to choose alpha? Yeah, choose alpha to be A0, A1, and AK. Then left side, right side is equal over this interval. All right, now this is A0, A1, A2, and AK. For alpha, I have determined their values. Now, let me determine the value for beta. Yeah, value for beta. Right. Next, I consider the second subinterval. Right? This is the first subinterval. Second subinterval. What is second subinterval? T1 to T2. Okay, T1 to T2. Second subinterval. Because what? Because S is in S and K. By definition, S is in C, K minus 1, A, B. Yeah. That means that take derivative on S. K minus 1 times derivatives continuous. Now, from here, okay. Now focus on this point T1. Okay. That means that P0, yeah, P0, yeah, polynomial over this interval. At T1 is equal to P1 at T1. You agree? Yeah. P1 polynomial over this interval. P0 at T1, because the S is continuous, so P0 at T1 is equal to P1 at T1. S has derivative of order K minus 1. So derivative, yeah, at T1 also same, yeah, also same. And so on. Take derivative K minus 1 times at T1 is equal to derivative K minus 1 times at T1. This is implies that move right side to left side. P0 minus P1 is polynomial at T1 is 0. P0 minus P1 derivative at T1 is 0, and so on. P0 minus P1 take derivative K minus 1 times at T0 is 0. Yeah, same. Okay. P0 and P1 polynomials of the degree K. A polynomial of the degree K at T1 is 0, derivative is 0, second derivative is 0, and K minus 1 derivative 0. Then is polynomial. It can be solved. Okay, P0, P1. Yeah. This polynomial is x minus T1 to the K power K multiplied by some number. Say, give a name to the number. Say B1, say for example. Polynomial of degree K at T0, at T1 is 0, derivative is 0. Derivative of until derivative of order K minus 1 is 0. Satisfy this condition, then the polynomial must be in this form. Suppose I know P0, P1, So I load this guy I load. Suppose I load P0, P1, so I load B1. It turns out that set beta 1 to be the B1. Okay, why? Okay. All right, now let me erase. Over this interval, S is P1. Yeah. Left side is P1. But here, this equation says that P0x minus P1x is equal to B1 x minus T1. Okay. So P1 is, let me see, move the P0 minus B1 x T1. Okay. It turns out that set is negative B1. So over this interval, S is T1. T1 is P0 x minus this. If I set beta 1 to be negative B1, then this equation, the right hand side, is also this. Yeah, equation of the right side. Yeah. A0 1 plus A1 x plus A2 x squared. A k x k. Then minus B1 x k. Yeah. This is a left side, right side. Yeah. About this equation, left side is this, right side is this. How about this term? X is in this interval, so this term is 0. Beta 2 times 0, and so on. Beta m minus 1 times 0. So this is what? This is A0 plus A1 x, A2 x squared plus AK. This is a P0 minus beta 1 x minus T1 truncated K. So see. Over this interval, if I set beta 1 to be negative B1, then left side, right side, same. Okay. This equation we have both A to T1. This equation is true. Now T1 to T2 also true. Now next, consider the interval T2 to T3. T2 to T3. The argument is very similar. Right. I don't have time, okay? I don't have time. So you can take a look at my notes. I hope my presentation here is helpful to you to understand the proof in the notes. Yeah, take a look in the notes. Okay, now we have a basis for this space. It's easy to do interpolation. I will show you examples next class on Wednesday. Okay. Now let's stop here. So go home to study my notes.